Right. So as you have gleaned from the activity that we did and the previous discussions that we've had, like leading up to this point in the course, we finally arrived at the lecture that really deals with kind of the meat of the scientific endeavor, and that is dealing with uncertainty. And specifically, kind of what we're touching on today is how not understanding uncertainty can lead us down the path of pseudoscience. So I on this title slide, I actually have two pictures which are meaningful and important. On the top one, this is an iconic scene from the movie Jurassic Park. Maybe I'm dating myself, but one of my favorite movies, one of the first I saw in the movie theater, when Jeff Goldblum's character is talking to Laura Dern about chaos theory. Chaos theory deals with randomness and uncertainty in nature, and so it's very much related. And the bottom here is a randomly generated pixelated image, and we're going to talk a lot about randomness and uncertainty and how that complicates things when we're thinking about science, and then specifically how that leads to pseudoscience. So, uncertainty in science. How possible is it to quantify how much you could be wrong? So we can actually quantify how wrong we are, right? That's something that we can do as scientists. And there are three ways that we know we can be wrong. The first is that nature has a lot of randomness, unavoidably. Things in nature are random. We actually, though, can predict randomness very well, empirically. Okay, so while things are random, and randomness can be complicated and confusing and difficult to understand, and you can't always predict the outcome, you can actually predict how randomly off the outcome will be. So we actually, at the end of the day, do know a lot about randomness. Okay, we know a lot about randomness, but nature is random. Number two, measurements and measurement instruments have limitations, right? So instruments are limited in their ability to perceive things, to observe things, and that introduces some level of uncertainty, some level of what we would call error, that we know what that error is, actually. For example, one of these ways in which instruments have limitations is their resolution. Can they see everything, every minuscule thing? No, they can't. We have to resolve them to see in increments or in grids on the Earth, for example, if they're a satellite. The third thing is that humans are interpreting data, and these interpretations may depend on assumptions, and those assumptions could be wrong. So every scientific, observation that we have, I don't know. For fuck's sake. All right, I'm back. I don't know why that always freezes. Oops. Oh, what a disaster. Sorry. All right. So, So the three ways in which we can talk about uncertainty in science is that, number one, nature is random. Number two, measurement instruments do have limitations. And number three, the interpretation of results of data may depend on assumptions, and those assumptions could be wrong. So two things that are natural follow-ons to this. The first is, can scientists know how wrong they might be in these ways? The answer is yes, of course. We can know a lot about how wrong we can be. We know a lot about randomness. We know about the instrument limitations because we designed them, presumably. And we have a good idea about how wrong our assumptions may be, although that one is the shakiest of the three. That's the one we know actually the least about, inherent in the fact that assumptions are assumptions. But at the end of the day, we do really know a lot about how wrong we are, actually. And is the uncertainty of scientific claims a problem? I would argue no. I think it's important that we identify what the uncertainties are. We are very well aware of what the errors may be, and we can quantify them very well. And so it's not a problem unless the uncertainty is not constrained unless we haven't spent time thinking about the uncertainty. If we have spent time thinking about the uncertainty, then I don't see the uncertainty of scientific claims as being a problem at all. In fact, I see it as being integral to the scientific process. So how does our misunderstanding of uncertainty ultimately lead us down the path of pseudoscience? Let's take the example of creationist accounts of Earth's history versus the scientific accounts. Can either of these be proven true? The answer is no. They cannot be proven true. And we talked about this, I believe, in class last time, that scientists actually don't set out to prove a theory true. They set out to prove the opposite of that theory not true. So, for example, if I say, I want to show that global warming is being caused by humans, I design an experiment that says global warming is not caused by humans. And if I show that to be true, right? If I show that global warming, or if I show that to not be true, right? If I show that global warming is not caused by humans, then I can infer, right, that global warming is probably caused by human beings. And the more I replicate this experiment, the more resolved I become in my conclusions. So I can never prove something to be true. I can only prove its opposite to be not true. Does that make sense? So I can prove something false. That's what I can do in science. I can't prove that it's true, but I can prove that something is false. So I can set out and say, the earth was created by God through the creation theory as described in Genesis. And then I can use science to say, that's not true. So then my inference from that is that the earth was not created by God. I can say that, right? The earth was not created in the way described in Genesis by God. Therefore, it must be this other thing. And I need other scientific claims to back that other thing up, right? I can't just say that without any backing, but that's how we do science. We prove the opposite of the thing we want to show to be not true. So let's talk a little bit about randomness, right? And the way we're going to talk about randomness is we're actually going to do an activity. We're going to do a coin flip activity, which I'm going to record a separate video for describing exactly how we're going to do that. But typically, right, or not typically, thinking about the ways in which randomness presents itself kind of in our world. One of the ways in which we can represent that is through flipping a coin. And so I will describe this activity in a separate video, which I'll also post after this one. Okay, so what distinguishes science then from pseudoscience? We're talking about uncertainty in science. We're talking about not necessarily being able to prove that something is true, but being able to show that something is not true or false, right? That's what we can do. That leads us to the question then, what distinguishes science? What makes something science versus something that's pseudoscience? We know it has a lot to do with uncertainty. We know it has to do with observations, right? These are all things that we've covered in class so far. But how specifically do we deal with these non-scientific claims? How can we distinguish that a claim is non-scientific? Is it empirical through the inductive method? Is there truth, absolute truth? Is it the explanatory power of the variable that we're talking about, or is it observational verification? No, says Popper actually in the readings that you had to do for today, it is actually falsifiability. Falsifiability. This is a very important term, which we're gonna talk about now. So what is falsifiability? Well, Popper says it's 7 things. Or he has like sort of these 7 tenets that kind of define the idea of falsifiability and what distinguishes science from non-science. So first one is, says Popper, it's easy to find confirmations for any theory if you're looking for them. This is known as confirmation bias. But confirmation should only count if they are the result of risky predictions, right? We would expect things to work out differently if the theory is untrue. Every good scientific theory is a prohibition. It says certain things do not happen. Therefore, a theory that is irrefutable, right? You can't say it's right or wrong. You can't, it's irrefutable. It just is, it exists on its own without any sort of empiricism, right? This is non-scientific. And this goes back to what I was just describing, right? That science is actually proving that the opposite is not true. So every genuine test, number 5, right? That's kind of what I've been saying. Every genuine test of a theory is an attempt to falsify it. So I take a theory, the sky is blue. Okay? What I set out to show in my scientific process is not that the sky is blue. It's that the sky is not blue. Okay, so the sky is not red. The sky is not orange. The sky is not green. The sky is not yellow. So therefore the sky is blue. That's a very simplified example of this, but that's the idea that we're talking about here, right? We have to be able to falsify our theory. This is what falsifiability actually means. Confirming evidence of a theory, right? Like stuff that would show that the theory that you're trying to show is true, right? Rather than the opposite of it is false, should not count unless it is the result of a genuine test that includes falsifiability. So it needs to have falsifiability in order for it to be a scientific theory, right? So attempts to rescue, for example, a failing theory by adding complications to it is just going to weaken its scientific status. If you overcomplicate things, right? If someone says, oh, well, this is not true because this thing, and then you say, okay, but also this thing, then it's weakening its scientific status. So we're dealing with confirmation bias here. We're dealing with risky predictions and falsifiability and showing that not that a theory is true, but that the opposite of it is false, right? These are all important tenets that distinguish scientific claims from non-scientific claims, or science from pseudoscience. And some examples of this are, of course, creationist science, astrology, and personality tests, similar to the one that you took today, as we saw in the one that you took today, right? Personality tests are pseudoscience. They run the risk of extreme confirmation bias. Oh, yeah, that's me. Yeah, that sounds like me. You disregard the things that don't sound like you. You think of only the things that sound like you. Therefore, it must be true, right? No, that's confirmation bias. There's no risky predictions here. There's no attempt to falsify what you're trying to show. There's no prohibition on this. It's not a good scientific theory. It's very weak science. It's what we would call pseudoscience or non-science. So let's talk about personality tests, right? So we took the short personality test here. You ranked it. I'm recording this video before you ranked it, but I'm assuming that most of you said that this matched your personality, close to 10 out of 10, or between, 5 out of 10 and 7 out of 10, 10 out of 10, right? It's very unlikely that most of you, unless you knew the trick, guessed 1 for this. And that's because of the Barnum effect, which is confirmation bias, essentially, right? So the Barnum effect is referring to the gullibility of people when reading descriptions of themselves. They tend to accept certain information as true, such as character assessments or horoscopes, even when the information is so vague as to be worthless. It's very easy to confirm something is true if you already think it's true. And that is what confirmation bias is. You already think it's true, so you set out to confirm what you know to be true. That's not science. Okay? That's confirmation bias. That's not science. The etymology of this word comes from the actual guy, P.T. Barnum, the circus guy, who famously declared, right, that there's a sucker born every minute. Part of his whole shtick was getting gullible people to buy into his mythologies. So we're not going to read this article, although it is posted to the Google Drive. But some things I want you to think about for next class when we discuss these is, why do people continue to be gullible? Why do we believe horoscopes? Why do we watch shows like Dr. Phil? Why do we visit psychics? Why do we visit faith healers? That sort of thing. Also, the article published in 1949 actually contains an example of a personality test with the exact same questions of the one the exact same questions from the one that you took are the ones that are included in this 1949 article. It's a very commonly read and discussed experiment. What about astrology? Astrology, unfortunately, I'm also a queer person. I know that in the queer community, for example, astrology is a big deal. Unfortunately, astrology is also pseudoscience, right? Confirmation bias runs very deep through astrology. There's no falsifiability. If something is wrong, then we just overcomplicate it to make it right. The last one here, so the attempt to rescue a failing theory by adding complications to it. So when the horoscope is wrong, we just make it more complicated so it's right? We kind of read into it. But where did astrology come from? It came from this guy, R.H. Naylor. So who is R.H. Naylor? Well, just to give you a little background on R.H. Naylor, he was a British astrologer who made a series of correct horoscope predictions and thus became famous. So shortly after Princess Margaret of England was born in 1930, he issued a horoscope for the new princess in the newspaper, and it was 3 columns, a lot of text, said her life would be eventful and that events of tremendous importance to the royal family and the nation will come about near her 7th year. Talk about vague. Talk about ripe for confirmation bias. So indeed, in 1936, when Princess Margaret was in her 7th year, her uncle, Edward, abdicated the throne, and her father, George, became king. Her sister, Elizabeth, would later become the queen, and she still is the queen. So therefore, events of tremendous importance to the royal family and the nation did come about in Princess Margaret's 7th year. Therefore, R.H. Naylor was hailed as a savant, as a genius astrologer, and astrology kind of took off. A week after he published Princess Margaret's horoscope, this also added to the allure, to the mystique, to the mythology. He issued a horoscope for everyone born in September, and it was kind of like all the craze, right? And then the next month, he issued another horoscope forecast. A British aircraft will be in danger between October 8th and October 15th. And then, indeed, on October 5th, which I guess is close enough to October 8th, the passenger airship R101, British airship, was wrecked in a storm and 48 people died. So I guess a British aircraft will be in danger between October 8th and October 15th. Instead of acknowledging that there is happenstance and coincidence, and October 5th isn't even between October 8th and October 15th, although if it was, that still wouldn't make this correct science, right? The confirmation bias was very strong. So the accuracy of this prediction and the Princess Margaret one and the horoscopes that Naylor published earned him a weekly horoscope column, and the rest is history. We're now totally infatuated and enthralled with horoscopes. And I admit horoscopes can be fun, but they're not science. They're pseudoscience, I'm sorry to say. But attempts to predict the future are as old as mankind, right, as humankind. For example, Nostradamus or Ptolemy, etc., right? So there's also some evidence that in strained economic times, people turn to horoscopes, which is probably why they took off in the 1930s, and perhaps why they're taking off again in this past 2 decades. And I found this zodiac signs of emojis, and I'm sure you can look at your emoji and be like, that's me. It's because we're all of these things all of the time, right? But it's so vague that it's really easy to find some confirmation bias in this. So which aspects of astrology are falsifiable claims then? And therefore, and similarly, what aspects of personality tests are falsifiable claims? How would you design a good experiment to test these? What is the difference between personal and anecdotal evidence versus scientific evidence? And what are the relationships between coincidence, correlation, and causality? I want you to think about these questions for next week when we get together and talk about these things, right? And remind yourself of Popper's 7 points here about the falsifiability of science. But I want to return to this coincidence, correlation, and causality for a moment and look at something that's a very fun website called Spurious Correlations. So oftentimes two variables appear correlated, like they have something in common because they're following the same graph, or when one thing occurs, the other thing occurs. Therefore, our brains assume, because of confirmation bias oftentimes, that the correlation is because of causality. But correlation between two variables does not imply or explain causality. And a good example of this is this graph here, which compares the divorce rate in Maine for every year from 2000 to 2009 versus the per capita consumption of margarine. So apparently, if the per capita consumption of margarine goes down, the divorce rate goes down, right? No. They just happen to be well correlated, but it doesn't mean that one begets the other, that there's any causality or any link between the divorce rate in Maine and the per capita consumption of margarine in Maine or in the US or anywhere. Like, none of these things have anything to do with each other, but they're well correlated. And so oftentimes our brains, absent the falsifiability of true science, will assume that there's some causality here, and this will lead us to the wrong conclusion. This will lead us down the path of pseudoscience. Okay, so that's the end of this lecture on pseudoscience and uncertainty and correlation and causality. Next week, we're going to tie things up by linking all of this to the pseudoscience that surrounds vaccines, and specifically the supposed links between vaccinations and autism, which is not, it doesn't exist, it's not a scientific claim, but is really popular, continues to be spread around in the mythology, and I think is very topical as we wait for a vaccine for COVID, right? We want to talk about the link, the pseudoscience link between vaccines and what people assume is caused by vaccines, which is autism, which it is not. And we'll use Popper's falsifiability claims, the idea of confirmation bias and spurious correlations and uncertainty to show that this example of a supposed link between vaccines and autism is, in fact, pseudoscience. All right.